Alright, so we're back for this simple workout example, except part 2. This is the exact same thing. I stole this diagram from myself. And the only addition here is a bias term, okay? The bias term is tacked on to the total input to a neuron, right? Once you compute the weighted input from all of the previous nodes or just the raw input, if this is an input node, you tack on this bias amount, B, and then that all goes through this transfer function sigma to get your output, okay? Now the derivative, when you take the derivative of the error with respect to W, it's going to work out exactly the same. All this stuff falls out just the exact same way, and then the very last step happens where you take the derivative inside with respect to whatever you're taking the derivative by. Now for this first case where we took it with W, then it's just the derivative of this with respect to W, which is just X, which is why this X falls out. In this case, we're taking the derivative of this, Wx plus B, with respect to B. That is just 1. Okay, so all we're left with is this first chunk here, which is the same exact thing as this, except with no X, okay? This is, and I've mentioned this before, but this is why people think of bias terms as just output from a node that always has value 1, okay? So there's always input there you can kind of push off of. Okay, so let me pause this and we'll go back to our plot window and add that in. Okay, so we're back to our window that we had. This is just where I left it from the previous video. I guess, I didn't think this through really, because now that I have a weight W and a bias B, I would like to call it B, but I'm already using AB for my XY coordinates for my training data point, so that's my bad. But let's pick something else random, like, how about Q? That's not Q. How about Q? Because that's not anything else obvious. 0 is fine, we'll leave it at 0. First thing I'm going to do is go back to my sigmoid function and make this Wx plus Q, right? Now I have a bias term. So you can see as I change this bias, it moves left and right, which is exactly what we would expect. Maybe it'll be easier to see if I make this really steep. If this is at -3 or something. I don't know. You can see here, right? The bias shifts it left and right. So I'm going to set that to 0. So that's in place. Now, I still have my delta W here. It's still based on my data point that I want to train on. Let me add in an arrow for the bias. Now there's a slick way to do that because the formula is so similar. Let me take this segment here, which is this arrow, and hit double to duplicate it. And it's the exact same thing, except there's no times A at the end, right? That times X in the original equation disappears, it's just 1. And I don't want to plot it on top of this one, so I'll plot it at, let's plot it at, I don't know, -1/2 for the X coordinate, just like that. Okay. And then let me add a little thing here. This is delta. I'm going to write delta bias. I'm not going to write delta B because it's Q. I did not think this through. Anyway, that's besides the point. So now I can adjust the bias, right? And it is not working. Oh. Okay, so in this expression, I actually have to write the formula. So I need to add the Q's in here. So it's not, I can't quite just copy it. Plus Q, okay. So let me just delete this and then reduplicate that first one that already has the Q's in it. Get rid of that. Put it at -1.5. All right, now we're talking. So you can see they're both not the same. They behave kind of similarly. both correspond to different things. So let's pick a value. So let's say 2 and 0.7. I'm sorry, that's really close. I want something that's worse. Let's go with like 0.4. Okay. So now let's start the bias at 0 and the weight at 1. Okay? Now you can see I have a change in the weight W, I have a change in the bias here, they're both negative, and so I will decrease each of them once. Okay? Now you saw I just flattened the curve and scooted it to the right. Okay? And I don't know if it's necessary for me to explicitly draw this parallel, but each time I click one of these buttons based on what this says, that's sort of like one pass through the algorithm. Does that make sense? You can't respond. Hopefully that makes sense. That's sort of like, okay, here's our updated computed value. That's my snapshot of what the gradient looks like. I make a small change in that direction, and then I look at it again, right? Every time I click these buttons, the arrows get redrawn. Whatever they say to do, I do. And at the moment, I need to decrease both of them. So let's just do this. So we decrease W, decrease the bias, decrease the weight, decrease the bias, decrease the weight, decrease the bias, decrease the weight, decrease the bias, etc. Now I'm just going to keep going. Decrease the weight, decrease the bias, decrease the weight, decrease the bias. Oh, went too far that time. Weight needs to go up, the bias needs to go up, and so then we're at this place where we just kind of hover around. I'm going to cheat a little bit and start doing them differently. 0.65, something like that. Okay, so now I can't see the little lines for either of them, so they're both basically 0. This is technically an overestimate because they're both pointing down. And there we go. I found the data point, and there's nothing else really to say. Now, where this will get more useful is when I start to have more than one data point. Now remember, if we bring this back up, that the error is a sum. Okay, so let me create a second data point, and adjust all of the equations, and I'll show them to you when I'm done, but I'm not going to make you watch. And then I'll plot both of the data points, and then we'll see how both of these play out. Okay. Okay. So you can't really see it because they don't exactly fit. I've added another data point. So this one right here is the original one. That's AB. This one right here is UV, right? And I can control it. Just like I can control the other one. All right, so let's make this 0.25 or something. You'll be able to see it, but I'm going to leave it a little bit off the screen. W and Q are the weights and biases, and they're both 0. And just for completeness, you can see I plotted the other point, and I've updated the little delta W and delta bias equations here. And I'll show them to you. So this is all the same as before. I have this derivative term with A's, B's. This is from the first data point, and then I have a minus, right? And then the exact same expression where all the A's are now U's, and the B is now a V, because the second data point is UV. And this, all I did is I copied and pasted it, and then did a replace in a text editor, and added that on here. Similarly, if you look at the bias, this is the exact same as before. The first expression with A's and B's. There's no times X here, which was an A. And then the exact same thing with U and B. And then there's no times U at the end, okay? So that's that. So let me start off with this pair of data points. Let me put the starting weight at 1, for example, and the bias is at 0. All right. Now that we have more than one data point, the error surface is much more complicated. You can see the derivative is twice as large just written out. And now we'll start to see differences between these two. For example, I think I can pick values like over here, where the weight wants to increase because, well, it thinks that that's the best way to go. The bias wants to decrease because it needs to shift back over this way. All right? So I'm just going to pick a random starting value, like 1 for the weight and 0 for the bias, and just start doing them and see what happens. So I'm going to do something a little bit smarter than last time. The derivative for W is large. The derivative for Q, which is the bias, is small. So I'm going to change W a couple of clicks down and then the bias just 1 to sort of emulate a more accurate representation of how backpropagation works, because it is proportional to the size of the derivative. Okay, so let's say W goes down, I don't know, 1, 2, 3 times. Bias goes down once. W needs to go down quite a bit, so 1, 2, 3. Did I just say bias? I don't know. Weight needs to go down quite a bit. Bias needs to go down. Weight needs to go down. 1, 2, 3. Bias still needs to go down. Weight needs to go down. 1, 2, 3, 4, let's say. Bias needs to go down some more. Now the bias is actually getting quite small. You can see it's sort of almost splitting the difference above and below with these, and all it really wants to do is adjust the weight to flatten out the curve, which makes perfect sense to me. So let's go 1, 2, 3. The bias still is a little negative and actually flips when I move it, so let's make it, I don't know, negative 0.9 or something. Shows me as a little over, but it's basically on the money. Now W is still negative, so let's keep pushing it negative. This still appears to be small. Weight still needs to go down. The weight still needs to go down. The bias needs to go up a little bit. So let's move the bias up. Weight needs to go down. It wants to push the bias up. Oh, that's probably too much. 7. Weight needs to go down. Okay, so now I'm getting into this region where clicking around is not fine enough. 1.8. Whoa. Sorry, too many of those. Move this down. My goodness. Anyway, this is hard to do with these little clicks over here, but you can see these are both very, very small. I have essentially pushed this line to go through both of those points. So now let's pick some new ones. Let's pick negative 3.5, something really big like 0.9. Weight needs to go way down, bias needs to go way up, and then let's move this first data point closer, let's say 1, and let's make it small like 0.2. Okay? So now it's saying I need to move the weight way up, which makes, way down, which makes sense because I want this to decrease to go through these points. Let me move the bias way down. This isn't really accurate. Right, the bias would be moving, the weight would be moving down, the bias would be moving up, weights go down, bias goes down a little bit, weights go down, bias goes down, weights go down, still, it just flipped. And hey, look at that, pretty good, right? These are both very small, boom, I nailed the points. And there you go, that's sort of the whole deal. Obviously the next extension to this would be you add one more node, one more data point, and you can see it'll sort of, with one more data point, you could construct them so that it's not something this curve can actually go through. And then you can see the algorithm hunting for the best solution between them, where all of the error is minimized in the way that we measure it, and it's just reached the limits. But recall, this isn't really a network. This is barely anything. This is a single neuron, single node, 2 data points. It can nail them every time. So the next real extension of this would be adding more nodes, which is a ton more weights, a ton more biases, and very difficult to graph. But hopefully this gives you a sort of nice physical, visual understanding of how that works. So let me know what you guys think in the comments. Ciao.